Start with questions about yesterday. You can ask me or I can ask you. Now, seriously, nobody has any questions from yesterday? Nothing? Nothing bothering you? Yes?
What kinds of neutron experiments can be done on thin films?
So the question was, what kinds of neutron experiments can be done on thin films? So many of those are done by reflectometry, and there's sort of an upper and lower limit to the thickness of layers that you can measure. I think there are lectures on reflectometry, right, Brian? Is that correct?
Oh, yeah.
So you'll see that. You can also do small angle neutron scattering experiments on thin films. That's been done, for example, on polymer films and nanostructured films. It's very hard to do inelastic scattering experiments on thin films because the volume of the sample is so small, so you have low signals. But some have been done, often by stacking multiple, for example, on membranes, by stacking multiple membranes in the beam and doing experiments that way. Other questions? Yeah?
What was the B and H field that you mentioned yesterday?
So when you apply let's talk about a current in a loop, right? That produces a field H, which magnetizes a material. So then you have the total B field, B equals mu naught H plus the magnetization. It's very complicated, but basically the way it works out is that you can think of a magnetization as being either a loop of current, and that causes magnetization, or you can think of it as being a bar magnet with a north pole and a south pole. And when you think through those arguments for a neutron interacting with the material, it turns out that it's always the B field that the neutron sees, not H, which would be produced by a circulating current, for example. It's quite a complicated argument, and you know, people can, I mean, when you think that Julian Schwinger and Feynman were debating this, you can tell that it wasn't an obvious or easy thing to solve. Other questions? All right, let's move on then. This was the last view graph I showed yesterday, which I talked about the difference between coherent and incoherent scattering, and pointed out to you the huge incoherent scattering from hydrogen, which is sort of a menace when you're doing small angle scattering because it's just a background, but is a friend if you're looking at vibrations of molecules in solids in elastic scattering. So it can either be useful or not. Okay, so now a little bit of math, and I'm not going to go through the details because what I want to do is to get you familiar with some terminology. You remember that when we looked at the, where was it? Here, I guess, at the partial differential cross-section, we had this expression, the product of two scattering lengths times this phase factor summed over all of the nuclei in the material. This phase factor being having in it Q, which is the wave vector transfer, and the distance, the vector distance between the two sites. So obviously we can rewrite trivially that phase factor as, just call it something else. It's called the structure factor, and is denoted in almost all of the literature by S of Q. So if you hear people talk about S of Q, that's what they mean, and you'll hear that a lot from neutron scatterers. If you go through some very simple algebraic manipulation, what you will find is that this S of Q can be written in this form. And this form has in it two important quantities. This thing called G of R. G of R is called the static pair correlation function. It gives you the probability that if you have a nucleus at the origin of your coordinate system, you have another nucleus at position R away from the origin of your coordinate system. So it's a vector. In general, this is a vector dependence, so it depends on direction. if you're in something like a fluid, simple fluid, like liquid argon or something, which is monotonic, then clearly that fluid is isotropic. And so this function only depends upon the magnitude of R. So once again, G of R measures the probability that two nuclei are separated by this distance. This row bar here is just the average probability. So averaged over time and space, if you like, what is the average probability that if you have a nucleus here at the origin, you'll have some other nucleus at position R averaged over time. So you see that in the case of a free liquid, for example, that's just the density of the liquid. So this thing in a liquid is just the density of the liquid. So when you measure S of Q, when you measure the structure factor, for example, in a liquid, and I'll show you an example in a second, what you're really measuring is the correlation between atoms in the material. And here's the definition of GR, the formal definition of G of R. But what you want to remember is this, spoken definition. It's the probability of finding atoms distance R apart. This is what G of R looks like for argon. It's deduced from this data on the left-hand side here, which is what S of Q looks like. You can vaguely see the data points here. And remember, the relationship between these two is just a Fourier transform. So if you measure S of Q, you can invert this Fourier transform and find G of R. So this is the G of R. What does it tell you? It tells you that the probability of finding two argon atoms separated by a distance less than the diameter is effectively 0. This ripple here is just due to the truncation, the fact that you don't have data all the way out to infinity and you're Fourier transforming it, so you get a ripple. So effectively, within a distance of the diameter of the atom, there's no probability of finding descenders at a distance less than that apart, which is obvious, right? And then at some short distance apart, there's a much bigger than average probability. The average is normalized to 1 here, so that some big distance, this is just the average density of the liquid, so effectively on this scale. And so you can see there's a first shell of atoms surrounding the atom you're thinking about, and then further shells out here. So that's what you measure if you measure S of Q on a liquid, for example. So let's come back. So this is what we've been talking about now is neutron scattering, and I showed you how to get this expression for the structure factor. We have to talk about something a little bit different in the case of X-ray scattering, because remember what we calculated before was this Thomson length, R0 here, and that was for a single electron. So if we want to figure out what the scattering is from an atom, we've got to add together the scattering from all of the electrons in the atom. That means that the scattering has to be integrated over the density of the electrons in the atom with this phase factor. It's the ubiquitous phase factor that we just mentioned before. Now, instead of having an argument which is Ri minus Rj, which is a distance between two nuclei, this is just the distance between two electrons in the atom. But it's the same formula. It's just summed over the electrons in the atom. This feature, the fact that you have to sum over something which is a spatial distribution, and Fourier transform it, means that the function you get in Q, this thing here, has a finite extent as well. In the case of neutrons, the nucleus really is a point as far as the neutron is concerned. So the Fourier transform of a point is a constant. In the case of X-rays, you have a distribution of electrons, so the Fourier transform of that is a distribution in Q space. Think of it, if you want, as the Fourier transform of a Gaussian is a Gaussian, and it has some width, which is determined by the width of the Gaussian in real space. this quantity, that this Fourier transform of the electron distribution is called the form factor. And so in neutron scattering, there is no form factor. It's constant as a function of Q. But with X-ray scattering, it damps. And in fact, this is what you can calculate for the form factor for various atoms in various states. You can see that if you have a point-like atom, which is what neutrons would see, then this form factor is essentially 1 forever. But in the case of X-rays, it damps as a function of the wave vector transfer and eventually goes to 0. That means that if you want to measure to very high Q in a diffraction experiment, you have a disadvantage with X-ray scattering because of the form factor of the atoms that are involved. I mean, you already know that synchrotrons have a huge intensity, so this is a penalty, but it's not a major penalty because they start out with so much intensity. But you should know about it. I'm not going to talk through this, but let me again describe what the result is. The interaction potential of neutrons with nuclei is a very complicated thing. It's a short-range, extremely strong potential. But because the nucleus is so small relative to the wavelength of the neutron, you can think of the potential being effectively just a delta function. And the effect of the potential is the same as the effect of a delta function potential. Those of you who've done partial wave analysis of scattering, maybe in physics classes, will know that if you have scattering from a potential distribution, if it's point-like distribution of potential, or delta function, that is to say, you only get isotropic scattering. You get so-called S-wave scattering. And there's only one number, actually two numbers because it's complex, but one complex number that describes that. So Fermi recognized that and worked out through what's called Fermi's golden rule for transitions between quantum states, and you can go through this if you care, that the effective potential inside a material for neutrons was just a delta function at each one of the nuclei multiplied by a bunch of constants here, and this b, which is the scattering length that we've talked about already. So why would we care about what this potential is, or this effective potential is? And the reason is that it allows us to calculate, hopefully, the refractive index of the material. And the way we do that is that we note that the definition of the refractive index, which is the wave vector inside the medium divided by the wave vector outside the medium. If you want to do that in wavelength, you can just invert this thing. But this is the standard definition of refractive index that you would find in any optics textbook. So what we've got to know in order to calculate the refractive index of a material for neutrons is what is the wave vector inside the medium compared to the wave vector of the neutron outside the medium. And that's just a conservation of energy argument. Outside the medium, the neutron has a kinetic energy, which is just h bar squared over 2m times the wave vector squared. That's just half mv squared, right? Inside the material, it has half mv squared, but with the v from outside replaced by the velocity inside the material, plus the average potential energy. And this average potential energy we can now work out by using this potential that Fermi taught us and adding that together for each of the atoms, each your nuclei inside the material, and just averaging it. That average gives us something called the scattering length density. It's just the sum of the scattering lengths of the nuclei inside some volume divided by the volume. Just like the mass density is the sum of the masses of things inside the volume divided by the volume. That scattering length density is the quantity that you will use if you're doing small angle scattering or reflectometry. And it is the one you will use because you're doing scattering at such small wave vector transfers that you can average the potential over many nuclei, right? In other words, you don't see, so for example, if you do sands from a polymer molecule, you don't see the positions of the individual atoms inside the molecule because you're measuring it with a wavelength of a scattering wavelength which is too big. So you just see an average of the distribution in the polymer, and that's specified by this scattering length density. So in terms of the scattering length density now, we can just take this average potential and plug it into this formula for the total energy inside of the neutron inside the material, and that has to be equal to the total energy that it had when it came into the material. And by equating those two, and then using this definition of the refractive index, we can find that the refractive index is given by this quantity here. So the refractive index for neutrons, because these B values are generally positive, rho is generally positive, so this quantity, the sort of refractive index, is 1 minus a positive quantity, generally. Yes? Not sure I understand the question, so I'm not going to repeat it for a moment. But
when you're calling rho as the scattering length density,
correct, yes.
rho actually has this scattering length. So it's just the average of the scattering length over the volume.
Correct.
So it's actually the energy scale.
That's right, it does set an energy scale. So the question was, does rho set an energy scale?
So how are you defining small b? Is it the minimum energy of the neutron?
So small b is the scattering length, but I could, you're right, because this rho goes into here as okay. So that's right. This is an average potential energy inside the material. So I could say that this is I could talk about this in terms of a potential energy, which essentially is what Fermi did, right? He's saying that the potential energy that the neutron sees effectively when it interacts with the nucleus is proportional to B. So yes, indeed. So I think what you said was another way of saying what Fermi was saying, namely that the potential that the neutron sees as it interacts with the nucleus is proportional to this number B, which is a length. Okay? Sorry, I didn't get it quite at the beginning there. This number turns out to be very small. This number, rho, is typically something like 10 to the minus 6 per angstrom squared. It's a length per unit volume, and so it has a dimension 1 over length squared. And if you plug that in and put a wavelength in angstroms, which is typically, a few, you'll see that this quantity here is of order 10 to the minus 5. So the refractive index of materials for neutrons is very close to 1, but is generally less than 1. What that means is you get external reflection of neutrons from materials. With light, of course, you get total internal reflection. It's what causes a rainbow, for example, internal reflection inside water drops. Here you can get total external reflection, but you can only get it at very shallow angles of incidence because, again, come back to your analogy about the potential with which the material is repelling the neutron, if you like, is so small, right? There's another way of saying it. So that means that you only get this reflection at very small angles, typically less than a degree. Typically. You can actually store some neutrons in bottles, but they have to have very long wavelengths, right? You have to have wavelengths that are hundreds of angstroms in order to store them in bottles. But it can be done with what are called ultra-cold neutrons. Okay. So here, I think I've said most of this stuff. Well, we'll just leave it at that for now. All right, what do we got next? Oh, for X-rays, there's the same thing. But what you'll generally see with X-rays is that the refractive index gets written in the manner at the top of this view graph. So it's 1 minus delta, which would be exactly the same as for neutrons if we identified delta with this lambda squared rho over 2 pi. And then there'll usually be an imaginary part. That imaginary part corresponds to absorption. So you imagine you have a wave function which is e to the I k r, right? If k has imaginary quantity in it, it will come out as I times I, which is minus, and will have a damping because it'll be exponentially damped. And that's done because with X-rays you have to include the absorption term, the damping term. But other than that, this is the two come out to be exactly similar, the neutron and the X-ray case, and the magnitudes are quite similar, within a factor of 10 at least. So again, X-rays can be reflected from the outside of materials. And you can make mirrors and lenses to do that for neutrons and for X-rays. So now let's talk a bit about diffraction. So in diffraction, what I'm thinking about is a beam of neutrons or X-rays which interacts with a crystalline material. Remember we talked about this thing, the scattering triangle. This is elastic scattering, so I've sketched here what the scattering triangle looks like. The incident wave vector and the final wave vector are equal because it's elastic scattering. There is a wave vector transfer here, Q. That's exactly what we drew before. And we almost always refer to the scattering angle, that is to say, the angle between the incident wave vector and the scatter wave vector is 2 theta. Be careful on that because, anybody, you'd think that it would be called theta, but it generally isn't. It's generally 2 theta. So the half angle here is theta, of course. And so that means that Q is equal to 2k sine theta. Right, so if you plug in the definition for k, which is just 2 pi over lambda, you get this equation. 2 pi over q is equal to lambda over 2 sine theta. So if you just invert this and multiply, cross multiply, you'll see you get k equals 2k sine theta. This 2 pi over q, 2 pi over the wave vector, is sort of the distance that you probe in the sample when you scatter radiation with a wave vector q. And you'll see people talk about that a lot. They'll say, in SANS, for example, they'll say, well, we're scattering at 0.001 reciprocal angstroms, so the length scale that we're probing is 2 pi over that, right? It's sloppy. It's good as a sort of rule of thumb, but it's sloppy and it's wrong in many cases, okay? So I just warn you that it's useful for thinking about things, but Fourier transforms don't work that way, right? You don't Fourier transform a point in Q space into a point in R space, point for point. It's true that what happens at very large Q influence, has a stronger influence on what happens at small r than it may do at other places in our space. But you have to be very careful with these types of sloppy arguments. One way of seeing that this is maybe true is this thing that if you imagine that you take an input wave like this and you draw lines of wave fronts perpendicular to this direction, and then you think about an outgoing wave and draw lines perpendicular to it, what you'll find is you set up a Moiré fringe pattern, right? And the separation of the Moiré fringe pattern will be this D, right? If you just work it out. And so the smaller the angle, the larger the spacing in the Moiré D pattern. If you have a larger angle, which is what's in this view graph, you can see there's the different angle. This is the angle here. Then the Moiré fringe pattern has a shorter wavelength, so you're essentially probing smaller D spacings. So you will see in the literature small angle neutron scattering, for example. Small angle neutron scattering means the angle between the incident and the scattered wave vectors is small. So you're basically probing large distances. You have to be careful in thinking, well, I'm probing exactly that distance, but it's generally true that you are probing large distances at small q. Then you'll see wide angle scattering. Wide angle scattering means that the period of the Moiré fringe is much smaller, so you're probing smaller spacings. So wide angle scattering will be something that you use to look at the distance between atoms or nuclei in a crystal, whereas small angle scattering will be something that you use to look at the conformation of polymer molecules, something which is much bigger. Another note of warning, everything that we've talked about up till now, even though I haven't done it formally, I've sort of introduced it in a somewhat hand-waving way, is something called the kinematic approximation. It's or the Born approximation, it's the same thing. So you'll see those words, kinematic approximation or Born approximation. It's essentially a perturbation theory. It does not include multiple scattering, right? So if I let neutrons interact with a sample of nuclei, for example, this approximation will only tell me what the single scattering is. That is to say, a neutron can only be scattered from one nucleus before I count it. That's clearly not true. I can scatter the neutron from one nucleus, and while it's still inside the material, it can scatter from another one. That's not included in what I've told you about. In many cases, that's okay, but it also means that energy isn't conserved. So this, in some cases, that turns out to be important, in particular for reflectivity experiments. For diffraction, which is what we started to talk about, generally this kinematic approximation is okay for bad crystals. What I mean by bad crystals. If a crystal is very perfect, then the probability of multiple scattering is much higher. Because if you're in a condition where you're getting reflection, you're getting scatterings from one part of the crystal, you are by definition in the right configuration to get scattering from a later part of the crystal. So the kinematic approximation, this stuff that I've told you about, is good if you have a bad crystal. A bad crystal means one where the orientation of the crystal in one part of the crystal is not the same quite as the orientation in another part of the crystal. So that's a sort of a word of warning. And in addition, this whole thing ignores completely the fact that the atoms might move when you're in real life and not just be fixed on their lattice signs. So it's sort of a useful approximation in many cases, but you ought to be aware of its limitations. I'm not going to go through this because it's probably not of huge interest to most of you, but let me just cite the general results. The general result is that if you have scattering from a frozen lattice of atoms, in other words, you put atoms on a regular array of lattice sites, like this cartoon character is doing over here, then you will only get scattering in particular directions, which are called, and that scattering is called Bragg scattering. And you'll only get that scattering if the scattering wave vector, Q, is equal in both magnitude and direction to a vector in the so-called reciprocal lattice vector, which is perpendicular to planes of atoms in the crystal, and whose length is equal to 2 pi on the divided by the spacing of those crystal lattice planes. So that means that you have to, in order to get this Bragg scattering from a single crystal, you have to orient the crystal accurately, depending upon what the incident wavelength of the radiation is. And this is just saying the same thing in different words. And rather than spend a lot of time on it, I'll just leave it at that. That it's the Bragg scattering is from the planes of atoms in a crystal. This is differences between real and reciprocal space for various structures. Again, you can go through that at your leisure. But here is what, as I say, this is the bottom line message. Each crystal structure gives rise to its own reciprocal lattice of points. And in order to get scattering, this Bragg scattering, you have to have a scattering triangle. This is your scattering triangle with a scattering wave vector which brings you exactly to one of these reciprocal lattice points. So you only get scattering for particular values of the wave vector transfer, both in magnitude and in direction, when you scatter from a single crystal. How many of you are going to be doing single crystal diffraction experiments? Yeah, okay. So this will be something that you'll need to worry about, and I'm sure your local contact will explain it in much more detail. I'm not going to belabor this, except to say to those of you who ever do single crystal diffraction, I get very annoyed with people who, or lots of us get very annoyed with people who don't use the correct nomenclature, because it's, the nomenclature was set up in such a way that it has a well-defined meaning, and you don't need to use a lot of words to describe what the meaning is. And then if you use the wrong type of brackets, then you can't understand what the meaning is. So if you're doing single crystal diffraction, please make sure you use the right nomenclature. Here's another way of thinking about Bragg scattering. If you think about an incident wave coming in on two planes of atoms, and you think about the phase difference between between waves that are reflected from this top plane and the waves reflected from the bottom plane, you'll get this condition, the Bragg law, Q equals 2k sine theta, and this Q in that case will be 2 pi divided by the distance between the two planes. So it comes back to exactly the same thing as I talked about a couple of moments ago. I pointed out to you that this kinematic approximation does not have in it the atomic vibrations. So how can we include that? Well, it's pretty easy, because what we're trying to do is Fourier transform a bunch of positions in a space. So we're just going to sum this phase factor over all the interatomic separations. And so if let's do it in one dimension. If the atoms weren't moving, then all I would have is delta functions with a scattering length density, a scattering length b at each atomic position, and I'm Fourier transforming that. That's what this means. Well, if the atoms are moving, what happens is they're all jiggling around left and right, because I'm using just a linear thing. And so to get that distribution around each probability distribution around each lattice site, what I have to do is to convolve this distribution with this triangular distribution here, which represents the distribution of the positions of the atoms while they're jiggling around. And so I've got now a Fourier transform of a convolution, and that, of course, gives me a product of two Fourier transforms. I get the Fourier transform of this thing times the Fourier transform of this thing. In other words, I get the same scattering as I got from a frozen lattice, but I have to multiply it by some Gaussian envelope, which is a measure of what the width of the vibrational distribution is of each of the atoms when they're vibrating around their official positions. And that's the meaning of this U squared average here. That's the mean squared displacement of the atom from its official position. And if you work it out, because you have 3 dimensions rather than just the one I'm doing here, you get this thing. And that factor is called the Debye-Scherrer factor. And that multiplies all of the intensities of the Bragg peaks that you get out of Fourier transforming this distribution. So when you make the measurement, the intensity of your peaks dies down at large Q vectors because of this Debye-Scherrer factor. Remember, it also died down because of the form factor. So you've got several things that are hitting you and stopping you making measurements of Bragg peaks at very high wave vector transfers. One way to get over that, of course, is to reduce the amplitude of this vibration. How would you do that? Cool. Yeah, it's hard to talk when you're drinking water. Yeah, just cool it. So you'll see that a lot of diffraction experiments are done with cold nitrogen sprayed on the crystal, for example. Okay. I think there's nothing. Well, this is Bragg's law. We've already talked about that. This is there are 3 sort of ways of looking at this. Bragg's law. This is the one that I have just talked you through, more or less. This is another one, the Laue conditions, and then there's something called the Ewald-Construction. I'm not going to try to talk you through that. There's a website here which has it's quite good, actually. It's a UK website. It's quite good, pedagogically going through description of diffraction, and I commend it to you if you you're interested in diffraction. So now we come back to this expression for the differential cross section, and then for this Bragg scattering, what does that look like? Well, it has this factor here, which is just the one we recognized. It's got the scattering length densities. It's got this phase factor. It's got the Debye-Scherrer factor in it, which is the thermal factor. It's got a delta function, which tells us that we can only get scattering at wave vector transfers equal to these reciprocal lattice vectors. And then it's got a normalization constant out the front. So basically what single crystal diffraction does is to measure the intensity of Bragg peaks and then to use this formula to try to deduce what the position of the atoms is inside a unit cell so that you can reproduce the scattering that you actually measured. So that's that game. And the X-ray case, the scattering cross-section looks almost exactly the same. It has these factors, which are exactly the same, and it has this factor which is for the polarization, average polarization of the X-rays, and then it has the Thomson scattering length. So there's really a very close parallel between X-rays and neutrons, and the numbers come out to be roughly the same, and the sorts of things you measure by diffraction are the same. We've talked about this. I'm not going to do that. So one thing you will come across, I'm not going to give you any real insights into it, but you'll come across this in all scattering experiments, and I hope you have lectures on this during the course, is this notion of resolution. Neutron scattering in particular is a signal-limited technique. That means that, and I showed you that at the beginning, that with synchrotron sources you could get lots of quanta, whereas with neutron sources you had many fewer. In order to get enough signal, what one tends to do is to relax the constraints. So we've talked up until now about a single wavelength of neutrons or a single wavelength of X-rays coming into a crystal and being scattered. So one wave vector going to one outgoing wave vector. In order to get any intensity, what is generally done is to make a distribution of wave vectors incident on the sample. And in that case, what happens is your scattering triangle gets smeared out so that your incident wave vector can have any tip it likes inside this box, and your scattered wave vector can have any tip within this box, and Q can be any wave vector which takes you from a point in this box into a point in that box. And what you do, the reason you have such a zoo of different instruments, right? A scattering experiment is in principle very simple. Take a wave vector in, measure the intensity of the wave vector out. But because of this issue of lack of flux and the fact that you have to relax these constraints in order to get any signal, what you tend to do is to relax the constraints differently depending on what you want to measure. So a small angle neutron scattering instrument looks very different from a backscattering instrument. You'll do experiments on probably both of those during your time here. What that comes down to is you pick this box at the end here to have dimensions, small dimensions in the direction you care about, and large dimensions in the direction you don't care about. If you're trying to measure small angle scattering, the dimensions of the box in this direction matter a great deal because you're trying to measure a small wave vector accurately. So it's no good having a large error in this direction. You won't be able to measure the wave vector well. So you tend to collimate the beam very strongly so that this transverse direction of this box is small. On the other hand, the length of this doesn't matter very much. So you tend to use something called a velocity selector. Those of you who are going down to Haifa to use the SANS machine will find it has a velocity selector, which is only a coarse definition of wavelength of the neutrons. So you make this box long in that dimension. On the other hand, if you're trying to do backscattering, you're trying to measure very accurately the change in energy of the neutron. In that case, it's absolutely pointless to try to do it if you don't know this length, because you don't know the energy of the incident neutron well enough to measure the energy change. So in that case, you tend to make this dimension very large, and this dimension, the longitudinal dimension, very well defined. So you'll find that all of the instruments have these sorts of compromises in them. And that's the reason why there are so many different types of instruments, because you make different compromises in order to measure different types of science. The point I wanted to make here is that even when you're doing diffraction, to measure the intensity of a Bragg peak, you don't just sit there. You don't just put your detector at one angle and your incident neutron coming in with one wavelength and one angle. You have to scan through the Bragg peak. right? Because you want to measure the intensity of something which integrates over this distribution of wave vectors. And because of that, you have to take account of these resolution corrections when you're measuring the intensity of Bragg peaks, and the intensity is modified depending on how you scan through the Bragg peak in reciprocal space. So the thing I want to make clear, want you to remember, is that resolution is always important. And so if you're making a measurement with any of these techniques, you have to understand what the instrument is doing to you. It will be distorting what you measure, and you have to understand how it's distorting it and quantitatively in order to be able to deduce the information that you want to get. I think I'm almost, yes, this is a good website. I actually checked it. So let me finish with this, and then we'll have a break. Remember that the form factor has, this is an e to the iq dot r squared, right? So it's a squared quantity. You have only information about the amplitude. You do not have information about the phase of the scattering. Right? Is that bad or is that good? Well, here's an example of something done by, calculation done by a friend of mine, Debye-Scherrer, who's at Oxford University in England. He took two photographs. This is a picture of a photograph of a guy looking at a mountain with some snow in the foreground. This is a picture of I think it's his niece, actually, an Indian girl. And he Fourier transformed both of those pictures. And he took the phase of one and combined it with the amplitude of the other. And, right, phase of A, amplitude of B, and then amplitude of A, phase of B, and then Fourier transformed them. And you can see he got these two results. I don't know why this thing is shaking, but anyway, it is. Maybe we're having an earthquake. You can see that this picture here, you can see more of the girl than you can in this picture, and you can see more of the man in this picture here than you can in this picture here. So which one has the phase information in, and which one has the amplitude? So it turns out that this picture here has the phase information from this and the amplitude information from that. And you can very easily see from this example that it's the phase that tells you where things are in the unit cell, right? In the picture. If you want a much better way of remembering that, then here's the one that Sunny Sinha put together. This is object A and this is object B, and this is the result of the two Fourier transforms. This one here, which resembles Darth Vader, has the phases from the picture of whatever that gentleman's name was, and the amplitudes from the other one. That's called the phase problem. So with that, let's stop and go get a cup of water or something, and we'll come back afterwards. Any questions while we're here? Okay. You want a break now, right?
Well, we actually have 2.5 hours.
I do?
Yeah.
All right, I can do it. Yeah, no problem for me. How about you guys? Okay? I want to get up and stretch, or calisthenics, or any of that stuff? Questions? So this phase problem is a serious issue. There are ways to overcome it. In particular, there are increasingly sophisticated ways with X-ray scattering of using boundary conditions and iterative computer procedures to overcome the phase problem and deduce the phases of the reflections. One way to think about that is if you made a measurement of the reflections, you can take the amplitudes, and then you can Fourier transform back to what you think is the distribution in real space, and you know that that you can set it up so that there should be no intensity outside the unit cell, and so what you can do is then take that throw away the intensity out inside the unit cell, and then Fourier transform back into Q space and use the phase factors you get from that in an iterative way to solve this. It's extremely computer intensive and was done for the first time less than 10 years ago. So I talked a little bit about single crystal diffraction. That's a diffraction from a crystal, from a material which is just a single crystalline piece. Very often what you have at your disposal is powder of very small crystallites. They're all representative of the same crystal structure, and in principle, if you've got enough of them and they're small enough, then every orientation of these crystals is represented inside your sample. That's a very powerful technique, it turns out, with neutrons. What you get from such a sample, instead of having Bragg reflections only in very particular directions corresponding to the orientation of the crystal, because you have all orientations of the crystal, you get Bragg reflections at a particular angle to the incident beam all the way around this cone. And those cones are called Debye-Scherrer cones. And that's what you measure with this technique called powder diffraction. So I want to talk a bit about small angle scattering now. I don't want to dwell on these typical applications, especially since we don't have any biologists here. I think we have some chemists, right? Maybe some polymer folks. Small angle scattering has been very important in polymer science. One of the early experiments, so you can think about how would you measure what a polymer chain looks like in a melt, right? You think of it as being, a plate of spaghetti. How would you determine what the average size of a piece of spaghetti is in a plate of spaghetti? Not easy, right? One obvious way is to paint the piece of spaghetti that you're trying to measure green and put it in a plate of white spaghetti, and then in principle you can see, which one is the chain you think about. So that was first done with neutrons, with a polymer. They put a few deuterated polymer chains of a polymer into a melt of hydrogenated chains of the same polymer. That turned out to be a bad thing to do because, as I've told you before, hydrogen has a huge incoherent scattering cross-section, which is background. So the fact that you had 98% hydrogenated polymer and 2% deuterated meant you had a huge background. So after they figured out that that wasn't the right way to do it, they used 98% deuterated polymer and 2% hydrogenated polymer. Pretty obvious now, but wasn't back in 1972. So they were able then to measure what's called the radius of gyration of the polymer, and to figure out how it scaled with the number of monomers in the polymer. So any of you who know about polymers know that there are various different scaling exponents which have been proposed or had been proposed before they were actually measured for this radius of gyration. So that was one of the first big impact neutron scattering experiments, SANS experiments, small angle neutron scattering experiments in the polymer field. So I won't bother with going through this, and I'm not going to talk about the resolution of SANS. Hopefully one of your other lecturers will talk about it. But be aware that it's a very important issue. You might ask, why are SANS instruments so long? You saw them. So who wants to tell me why SANS instruments are so long? Yeah. That's right. You need to have, because you're trying, so the question, well, he answered the question. So you're trying to measure a very small scattering angle, And if you're trying to measure a very small scattering angle, you want a very well collimated beam and an accurate measurement of the angle of scattering of the scattered beam. But why 20 meters? Yeah.
Because the angle is so small that the longer you have this distance, the more
Completely right that you know, if you want to tell the difference between angles, it's easier to back off a long way because the distance between the subtended is greater. But why can't I just have, you know, a smaller sample, a narrower beam, and a shorter instrument? So another way of saying that is that you can't get the resolution on the detector, right? So when SANS instruments were first built back in the 70s, the best resolution that you could get on a position-sensitive detector was about a centimeter, and so you were constrained by the size of the pixel on your detector to have something about a centimeter. It was also true that a centimeter was about the right size for a sample. You could get enough scattering from that you could see. If you have a square millimeter of sample, you'll get 100 times less scattering, right? And whatever size detector you put it on, it's still 100 times less scattering. So that's an example of this general principle that you make these instruments at neutron scattering centers to compromise between various factors. Now it turns out now that that we've subsequently learned how to build detectors with 50 micron resolution. So why aren't we using that for SANS instruments? I don't think I know the answer to that, actually. I think there's some thinking that ought to be done about how to do that better. But because what happens is you get trapped in old ways of thinking and you think, oh yeah, we just make it long. Well, is that the right thing to do? It's not obvious. There are probably other ways. So the point I want to make is that resolution is important. How you build the instrument, what sizes of samples and distances you choose are influenced by this concept of resolution. I'm going to do one more. You want me to stop now, or you want to? Oh, let's go take a group photo. I'll stay here.